Okay, now let's get ready for the second part of our, that is derivative basics part number 2, part 2, and we're going to talk a lot today about a little thing called the power rule, which is going to make it a lot easier than doing your definition of derivative and your difference quotient. Now, first little theorem I have here states that the derivative of a constant is 0. Notation-wise, this is read as the derivative with respect to x of the constant c equals 0. Okay, so what does that mean? Well, here's what it means in this example. If I have a function f of x equals 7, that is called a constant function. Why is it called a constant function? Well, because if I graph f of x equals 7, so 1, 2, 3, 4, 5, 6, 7, I know that is a horizontal line. That is what a constant function looks like. And again, if you draw better than I do. In this case, no matter what my x is, my x could be out here at like -5 or something, the y value is still 7. I could be at x equals 2, something like that. Y is still 7. My y value is constantly 7. Now again, when we talk about f prime, we're talking about the slope of the tangent. So what is the slope of this line? 0. If your line is down here at y equals -8, again, objects on this PowerPoint may not be drawn to scale, but again, constant function, this is the equation y equals -8. What is its slope? 0. That's what this is saying. Okay, now you have it, the power rule. If you remember before, I gave you a function like f of x was, I believe it was x squared plus 1 earlier in part 1 of this lesson, and we did the definition of derivative and all that, the difference quotient, and we found when we did the difference quotient that we got f prime is 2x. Using this equation, I can do this in a matter of seconds, no limits, whatever needed. Here's the basic idea. So what this is saying is the derivative with respect to x of x to the power n. So if I have some variable x raised to some power, I do two things. Number one, if you'll notice, I move the power to the front. And then secondly, my power was n. I subtract 1 from it. And yes, so if I were to do this, let's follow that same logic here. F of x is x squared plus 1. F prime, move the power to the front. That gives me 2. Keep the x. Reduce this by a power of 1, so that gives me x to the first. And the derivative of the constant is 0. I get f prime is 2x. Which we did in a whole lot more steps using that definition of derivative and the difference quotient. All right, that's the basic idea. Now, again, my thing is, I don't like you just knowing shortcuts and stuff like that unless you know where they come from. I promise you there is a proof coming for this. I do need to first teach you how to derive logarithmic functions, specifically the natural log. And then, yes, I do promise I will prove this for you so you understand where it comes from and why it works, not just here's a formula, do your thing. My personal favorite version of the power rule is this. Say I've got like a constant in front, like say I got something like this. Let's say I got f of x is like 3x to the 5th. So not just like x to a power, but a coefficient in front. I actually take the 5 times the 3, so I take the power times the coefficient, keep the x, and then drop a power. Much nicer than the difference quotient. That's basically what I'm telling you here. Okay, some basic examples. This one, it just always reminds me of that that old beer commercial, you know, I don't always do whatever, I choose to drink whatever. So here's like, I don't always derive, but when I do, I choose the derivative of x squared. Dos Equis. Okay, dumb joke, but we calculus folk have our limitations in the humor department, I guess. But yeah. Again, why is it 2x? 2 goes to the front. Keep your x. Drop a power. There you go. Derivative with respect to x, x cubed. 3 goes to the front. Keep the x. Drop a power. Same deal here. 4 times 5, 20. X to the fourth becomes x cubed. Here, power to the front, 8 times negative 3 is negative 24. Drop a power, 7. That is how easy this power rule is, and it's pretty cool. But again, I'm going to make you earn it. I'm going to make you figure out, and we're going to prove where it comes from. Okay, here are some ones. If you want to pause the video and play a little bit, I will let you see what you can do. Okay, so we'll start easy. Basic power rule. 3 times 5, or 7 times 5 is 35. Keep the x. Lose a power. Easy as that. 3 times negative 19, negative 57. Drop a power. Squared. See, the power is negative. Doesn't matter. Move it to the front. X. Now here's where a lot of people are going to mess up. When you subtract a power, when you lose a power, you're actually subtracting 1. That does not equal negative 8. It equals to the power negative 10. Now, I like deriving it when it's a negative power. For my final answer, I hope you remember that when a power is negative, it actually makes the reciprocal. Now, since the 9 does not have a negative power, it's going to stay. But this x to the negative 10 is going to move to the bottom and become x to the 10th. So I like using the derivative with the negative powers if they exist. But my final answer, I actually move the negative power to the bottom. Same deal here. I've got derivative with respect to x, 1 over x. That is the same as saying I'm going to derive with respect to the x to the negative 1 power. 1 over x to the negative 1, same thing. I prefer the form with the negative power to derive, and then we'll bring it back into rational number form for the final answer. So move the negative 1 to the front, keep the x, drop a power. Negative 2 minus 1 is negative 2, which gives me a final answer of negative 1 over x squared. Same basic idea here. Derivative respect to x. This is not a fun way to derive, so I'm going to rewrite it using the negative power, which gives me negative 100. Keep the x. Negative 100 minus 1 is the negative 101, and negative power to the bottom. Easy enough. Here's where it gets a little tricky. This is going to be the same as saying derive with respect to x, coefficient pi times x cubed. So I move the 3 to the front, which gives me 3 pi times x. Oops, that would be to the negative power, so that's negative 3 pi times x. And x would become to the power negative 4. And then I rewrite it. The negative 3 pi on top. X to the fourth goes to the denominator. That's basic power rule. Again, can I make it harder? Yes. Am I going to? Most certainly I'm going to. Oops. Pay no attention to this answer key. That's x to the 10th down there. We've already done that one once. And yeah, that would be to the negative 10. Forgive me, Father, for I know not what I do. Okay. Couple of properties of derivatives. This is basically saying if I'm taking the derivative of a function f plus a function g, all I do is derive f, derive g, and just add it together. Same holds true as subtraction. The derivative of f minus g, derive f, derive g, subtract the 2. Here's an example. In this case, instead of just deriving one term, I'm deriving a whole polynomial. So take it term by term. So what does that mean? Derive this, derive that, derive that, derive that. 4 different steps. Now, that being said, this step that I've written here, I normally wouldn't write just because doing the power rule in your head is so easy. I can take the 3 times the 5 and get 15, drop the power. So my hope is that you can go straight from here to your final answer, but this is the actual process that's going on, deriving it term by term by term. And you say, well, what happened to the 3? Remember, this is a constant. That is a zoomed out or zoomed in here. And we know the derivative of a constant is 0. I just didn't see fit to write plus 0 on the end because 8 plus 0 is still just the 8. Okay. Let's get into some actual word problems here and start applying some of this derivative things like what does it do for me. So I'm going to start with an object is dropped from the Empire State Building that is modeled by the equation 1250 minus 16t squared. Again, initial height of the building. This is your accounting for gravity, which is negative 32 feet per second squared. And again, this goes all back to like your particle motion formula, you know. So that's where it comes from. And h of t is measured in feet and t is in seconds. If we're doing this in meters, you know, this would be like a negative 4.9, such like that. If you do 1/2 of the force of gravity, stuff like that. I want to find the velocity function of the graph, of the object. Find the instantaneous velocity at t equals 5. Find the time interval over which the function is valid. And find the velocity when it hits the ground. You may say, well, that's easy. That's 0. When it hits the ground, the velocity is 0. No, not necessarily. We'll get into that. So let me show you how this is going to play out. So I start with my height or my position function. And again, if you've taken a physics class, you probably talked something about, like, especially if you've taken a physics C class, calculus-based physics, you probably learned that the derivative of position is velocity. And again, derivative of a constant, 0. Derivative here, move the 2 to the front. Negative 16 times 2 is negative 32. Drop a power. There's your velocity function. Part B, I think I asked you for the instantaneous velocity at t equals 5. So I take my velocity equation, this is my v of t, evaluate it at 5, or I could have just called it v of 5. So h prime, v, same deal. And all I did was just plug 5 in for the t. So basically, the instantaneous velocity at time 5 seconds, I know that it is going downward at a velocity of 160 feet per second. So that object is really hauling some tail right there. Okay, now determine the time interval on which the function is valid. I mean, obviously, if you drop it, you know, we're not going to do negative time. We're not going to ride that train doing like the Back to the Future stuff. And there's going to come a time where this object stops moving. So there is a starting time, there is an ending time. So I'm looking mostly at the time when it's dropped and the time it hits the ground. The initial time, that's easy for my domain. 0. The final time, we have to find when the object hits the ground. In other words, when my height is 0. So I'm not going to use my derivative function for this. Again, I'm not trying to find an acceptable or a reasonable domain for the derivative. I'm trying to find it of the function. So I'm going to set the height off the ground or the position equal to 0. Going to move the 1250 over, divide 16, square root both sides. I'm going to approximate it out to 2 decimals. However, on your AP Calculus test, please use 3, as the graders will also do that as well. So basically, my domain for this function is times 0 is when the object is drawn until approximately 8.84 seconds. That is your domain. That is how long this object is in the air if you drop it off the Empire State Building. Okay. Part D, velocity when it hits the ground. Again, some people say, well, when it hits the ground, the velocity is 0. No, if the velocity is 0, people wouldn't die when they jump off of high buildings. It's going really, really, really fast. Now, the problem isn't that the velocity is 0 when you hit the ground, because it isn't. Your velocity is it's very high. The problem is that you go from that very, very high downward velocity to 0 very quickly. That's where the damage comes in and why you don't want to do that. So basically what I want to do is this. Here is my derivative function. Again, my time, that's the time when it takes to hit the ground. So basically I'm evaluating my velocity, which is my h prime function, which was negative 32t, and it hits the ground at 8.84 seconds. So yeah, at that time when you first hit the ground, that object is going about negative 282.9 feet per second. And then it's going to come to a screeching halt, which means that object's going to probably be pretty flat by the time it's done. Okay. Couple of basic power rule play with stuff here. F prime on this first one. Move the 6 to the front. Keep the x. 6 minus 1 is 5. Easy peasy. A positive times a negative 9 is negative 9. X, drop a power to the negative 10. 12x to the 5th minus 9 over x to the 10th. Again, negative powers make reciprocals. So that's why the x to the 10th goes to the bottom. Find dy dx, it means to derive. If my function is called y, I'm finding y prime. If my function is called f, I'm finding f prime. So that's what, 24x to the 7th, 10x to the 4th, plus, okay, imagine that as like a power of 1. 1 times 6 is 6. And then you keep your x and then drop a power. That makes x to the 0. Hope you remember from algebra that numbers to the power 0 equal 1. So 6 times 1 is 0. Plus a constant, and we know what happens when you derive a constant. It's 0. So far pretty easy. And then there was this. Okay. Again, a little knowledge of algebra goes a long way. Hopefully you remember that the square root of x is the same as the 1/2 power of x. So now I can use my power rule, move the half to the front, and then subtract 1. This gives me 1/2 x to the negative half. Now, if this were a free response question, and this is way, way, way too easy for a free response question, by the way, you could just stop right there. That being said, it is not a free response. I am not going to stop there. I want to show you what an answer might look like on a multiple choice. So this is going to give me, I got the 1/2 times, again, I have this negative power, so it's going to move to the bottom, which gives me a 1 on top, and then a 2, and then x to the half is root x. This is something you should memorize. It's something I know by the back of my hand. If you ask me what is the derivative of square root of x, it's 1 over 2 root x, and then we can throw in some constants and stuff as well, but pretty easy stuff so far, just a little unusual. Okay. Number 10. At what point does the graph of this y equals x cubed minus 3x plus 4 have a horizontal tangent line? Let's talk about it. I'm going to draw like an upside down parabola here. This is what a horizontal tangent line looks like. In other words, the slope of the tangent would be 0, which means basically whenever I see horizontal tangent line, if this is called y, this basically means find when y prime is 0. If this was called f of x, then I would want to know when does f prime equal 0. So horizontal tangent you can do in two things. Number one, so when I see horizontal tangents, number one, that means I have f prime or y prime or some prime. Let me just put it this way. You're basically going to find the derivative, and then secondly, set it equal to 0. So, start with, again, what do you know about the slope of a tangent line? Slope is 0. So, here's my y. Hopefully you can power rule that and get your y prime. Derivative of x cubed is 3x squared. Derivative of negative 3x is negative 3, and the derivative of the constant is a big fat 0. Now I'm going to set it equal to 0. So here's the tangent slope. To be horizontal, I need the slope 0. And then I'm going to solve for x. Okay, so I get 3 equals 3x squared. Divide both sides by 3. I get 1 equals x squared. Square root both sides. Square root of x squared is, let me go ahead and add some steps here. So square root of 1 is 1. Square root of x squared is absolute x. So to solve it, give me all points that are a distance of 1 from 0. That answer is both plus and minus 1. Now here's the question though. In this problem, let me go back. Did I ask you find the location or did I ask you for the points? Which means just finding that x value is not good enough. I need a y. So again, our equation was y equals x cubed minus 3x plus 4. So what I'm going to do is basically I'm going to plug in, I'm finding what y is at x equals plus and minus 1. At 1 I get 2, at negative 1 I get 6. So my horizontal tangents occur at the point 1, 2 and negative 1, 6. Nothing to it. Okay. F prime equals, well, that big ugly thing starting with 3x to the 4th. Find F prime. Wish granted. Me and the power rule. It's my boy. I gotcha. Move the 3, so negative 6x squared. Move the 2, 2x. Derivative of negative 4x is negative 4. Derivative of a constant 0. F prime is done. Whoa, wait just a stinking minute here. What is this tomfoolery? What's this witchery going on? Yes, you can take multiple derivatives. You know, I talked to you about earlier that the derivative of position was velocity. If you derive that again, you get acceleration. So basically, I know that if I take a position function, x of t, I would have to derive that twice to get acceleration. So you can do multiple derivatives. So that's what we're going to do. To find f double prime, the second derivative, I basically prime the prime. Move the 3 to the front, that's 32x squared. Move the 2, negative 12x. Derivative of 2x is 2. The derivative of the constant 4 is a big fat 0. F triple prime, guess what? We derive again. 72x minus 12. Fourth power, derive again. Derivative of 72x is 72. The fifth derivative, derive the constant 72, 0. And any derivative after that, yes, I go 6th, 7th, 8th, 9th, 10th derivative, whatever, would be 0. Okay, a couple of last terms here, and then we'll end this. I want to talk to you about the normal line. You know, maybe in physics you're used to something. Maybe you got like an inclined plane here, something like that, and you got some force acting on it, you know, going up the up this line, moving it. You probably heard something called normal force, which is like when a force comes down perpendicular to like your path here. So basically normal force is perpendicular. Same deal here. When you hear me talk about the normal line, I'm talking about a line perpendicular to the tangent line. So if this is this blue, if that is my tangent line, this would be my normal line. So it's kind of like your normal force. It makes a perpendicular with the tangent line. Okay, so evidently I already animated that in my slides. My bad. Pay no attention. Nothing going on here. Nothing to see. There we go. Okay. Here's a little graphic showing some things that I think are kind of important. Probably a good thing to write down in your notes. So, again, here I have a line segment connecting 2 points on the curve, rise over run. That is called a secant line. To find its slope, it's, you know, y2 minus y1 over x2 minus x1, or f of b minus f of a over b minus a. Same thing. It's what you learned how to do in Algebra 1. Tangent line, right here. How do I find its slope? Well, you can use like this and then use that whole limit as like b approaches a and go with like the whole definition of derivative, all that jazz. No, thank you. Its slope is just f prime. And then our normal line, again, remember like in algebra when we talked about lines being perpendicular, if slope number 1 was like a over b, then the slope of the perpendicular was the negation of the reciprocal. So if the slope of the tangent line is f prime, slope of the normal line is the reciprocal negated, 1 over negative f prime. Okay, I think this is the last example. I want you to find the equation of the tangent line and the normal line. Now here's the cool part. Again, it's y minus y1 equals your slope times x minus x1. So for the tangent line, that's going to be y minus, well, hell, I got my y coordinate right there. Slope of the tangent, we'll get to that later. My x is -1, so minus -1 is +1. When I do my normal line, I'm still going to have the same y minus 4. I'm still going to have that x plus 1. The point of tangency is the same. I mean, it's by definition, you know, you got a curve here. Here's my tan line. There's my point of tangency. The normal line intersects it at the point of tangency. So they're going to share that same point. The only difference is finding the slopes. So I'm going to first find f prime, which is my slope of my tangent. We'll deal with that normal line stuff later. So, do your power rule. 2 times 2 is 4x. Derivative of 3x is 3. Derivative of the constant 5 is 0. So then f prime of x is 4x plus 3. But I don't want f prime of x. I want f prime at the point -1. Which is 4 times -1 plus 3 Negative 4 plus 3 is negative 1. Tangent line, done and done. Again, this is your tangent slope. To find your normal slope, I usually notate that as m norm. I'm going to take the negative 1 over f prime. So it's negative 1 over m tan is negative 1. Normal line has a slope of 1. Game, set, and match. I do have one last little present for you. Given that the derivative with respect to x of f of x is f prime, derivative of y is y prime, what is the derivative of Optimus? Yeah, those of you guys that are Transformers fans, you get it. If you do get it, you say, oh God, that's really awful. Again, calculus humor, I do my best. Hope this helps, and I hope you learned something, and I hope this makes sense. See you later.